In this last exercise, we're going to talk about projectile motion. So we've seen projectile motion before, and we looked at it mostly in terms of vectors in the Extension 1 course. And we found that with a projectile, when there's no air resistance involved, that we ended up with a parabola. So the projectile is fired up at a particular angle, so it might be alpha, with an initial velocity, and it flies up, reaches maximum height, comes back down, and that's just a normal parabola. Now, if there's some air resistance, it's not going to work exactly the same. Air resistance is going to slow it down. Now, air resistance is always opposite the direction that it travels in. So horizontally, air resistance is going to be negative, it's going to go to the left. Vertically though, when the projectile is going up, the air resistance is going to push down along with gravity. But once it reaches its maximum height, it starts going down again, the air resistance is now going to go up. So the air resistance is always in the direction opposite motion. So if there's air resistance, it's going to start off in the same angle with the same velocity, but it's going to be slowed down by the air resistance, and it's going to come back down a little bit sooner. Now, this is where the air resistance is proportional to its velocity. If it's proportional to the square of velocity, then the air resistance is much more intense, and it's going to come down a lot faster. Now, what you are going to find is this air resistance is so much at some point that it almost comes down vertically. And there will be questions that ask you about what's that maximum possible horizontal displacement, which is just finding the limit as t goes to infinity. So one thing you will find too is that the maximum height is going to be a little bit further over, because this air resistance is really going to make it drop off at the end. Now, a lot of these examples only really ask information until it reaches its maximum height, but you can certainly get another example, and when it's on its return journey, then you do need to come up with that other equation for the air resistance, where changing the direction of the air resistance so the direction is opposite the motion. So if we look at our resistance vector as being k times our velocity vector, so in this case I'm proportional to velocity, then let's look at the forces we could have. So our horizontal force is going to be negative k times the velocity in the horizontal direction. Negative because it goes against our motion. Now, this k, this is a force, of course, so m times acceleration. You can, of course, divide through by m. K over m could just be a different constant as well. So you do actually get some examples sometimes where this m gets absorbed into the k a little bit. Really, if it's numerical, then they're going to just divide. Okay, now our vertical forces depend whether we're going on an upwards journey or a downwards journey. In both cases, we do have gravity going down, so negative m times gravity in both cases. When we're on our way up, then our air resistance is pushing down, so that would be negative, so minus k times our vertical velocity. But when we're on the downwards journey, as we're going down, the air resistance is pushing up, so it's in the opposite direction of the gravity, so plus k times velocity. Interestingly, over 3 different textbooks, out of all the examples I've looked at, none of them actually take this into account. They're all just using this one. So one of the things you will notice here is in Extension 1 we mostly did this in terms of vectors, but here I've very much separated out the x's and the y's into separate equations. It's just easier to work it out because it depends what we're looking for. But for the most part, we're going to be doing it with respect to time. So the most part, our acceleration is going to be the derivative of velocity with respect to time, which actually works really nicely here, everything with respect to time. In this first example, we're just looking at it numerically here. So there's a particle projected from the origin with initial speed 30 meters per second at an angle of 60 degrees above the horizontal. It's subject to gravity. We're just going to use 10 meters per second squared, as well as air resistance proportional to its velocity with k equals 1/6. Find the equations for the velocity of the particle in parametric form. Okay, let's start by looking at our initial situation. So initially, when t equals 0, it's projected from the origin. So our initial horizontal is 0 and our initial vertical is 0. Let's draw a little triangle for how it's being fired. So it's 60 degrees to the horizontal at 30 meters per second. So this one, of course, is 30 cos 60 because that's adjacent to the 60, and this one will be 30 sine 60. Cos 60 is half, so that one's 15. Sine 60 is root 3 on 2, so the on 2 makes it 15 root 3. So those are our initial velocity components. Now let's have a look at our initial force. So we're just going to assume actually the particle has a mass of 1 unit. I forgot to write that in the question, sorry. So 1 kilogram. So often they say unit mass. So in that case, our force is m times acceleration, just 1 times acceleration, but let's write that. So horizontally, it's going to be negative k times its velocity, and I'm going to use that x dot notation for its velocity. Now, vertically, I'm only considering the upwards equation here. So its mass times its vertical is equal to its negative m times g minus 1/6 times its vertical velocity. So those are my equations here. Now, because m equals 1, then x dot is negative 1/6, x double dot, sorry, x dot, and this one is y dot equals negative 10, because we said 10 for gravity, minus 1/6 y dot. Now I'm just going to do this with respect to time. So this acceleration here is the derivative of the velocity with respect to time, and that equals negative 1/6 x dot. Let's separate our variables. So dx dot, let's bring the x dot down. I'm actually going to take the 6 up because a fraction's a bit annoying, equals negative dt. And we'll integrate that. And the time starts at 0 and goes until time t. And its velocity, remember our initial horizontal velocity was 15, and that's going to go until our final velocity, whatever that is. So let's integrate that. So on this side we have 6 times the log of x dot from 15 up to x dot equals negative t from 0 to t. Okay, I'm going to use that little shortcut I've used before on this one because it's 6 times log of x dot minus log of 15, and then using my log laws, that's the same as x dot over velocity over 15. And plug in t, I get negative t, plug in 0, I get 0, so that's just minus t on that side. Now I do need it to be x dot equals, velocity equals. So I'm going to divide by the 6. So log x dot on 15 equals negative t on 6, e of each side. So x dot on 15 equals e to the negative t on 6. X dot is equal to 15e to the negative t over 6. So that's our horizontal velocity equation. Now let's look at our vertical equation. So again, I'm just going to do it with respect to time. So my vertical acceleration is the same as the derivative of my velocity over time, equals -10 minus y dot over 6. One thing to make this a little bit easier is I'm actually going to, when I separate variables, I am going to multiply each side by 6. So dy dot times 6 equals -60 minus y dot dt. I might leave the negative on this side, so 6 dy dot over 60 plus y dot equals -dt. Integrate each side. So again, let's work out what those endpoints are. Again, t starts at 0 and goes to t. This is our vertical velocity. So it started at 15√3 and goes up to whatever its velocity is. So this is a log. So log of 6 times log of 60 plus y dot from 15√3 up to y dot is equal to -t from 0 to t. Let's plug in our endpoints. So 6 log, again I'm going to do that division thing because I'm minusing logs, over 60 plus, what have I got, plus there, good, yes, 15√3 equals -t. Let's divide by the 6, so log of 60 plus y dot over 60 plus 15√3 equals -t on 6. E of each side, so 60 plus y dot over 60 plus 15√3 equals e to the -t over 6. I'm going to times by this thing, I'm going to subtract the 60. I just want to do a little bit of a shortcut just because I'm running out of space, but I want you to finish that equation yourself and show that it is equal to 15 bracket, another bracket, 4 plus √3, close the bracket, e to the -t over 6 minus 4, close the bracket. In part B, we're asked to find the equation of the horizontal displacement. So this was our horizontal velocity. So our velocity, of course, is equal to dx dt, which is 15e to the -t on 6. So dx equals 15e to the -t on 6 dt. Let's integrate that. So x started at 0 and goes until x, and time starts until 0 and goes until its time. So let's integrate. So that's x from 0 to x equals, I need to divide by the -1 on 6, so I'm going to multiply by -6 instead. So -6 times 15e to the -t on 6 from 0 to t. This is just x minus 0, so x, that's -90 e to the -t over 6 minus a negative, so plus 90 e to the 0. Let's just factorize that as well. So 90, I'm just going to write this one first, so I'm a positive. So 1 minus e to the -t over 6. So part C says find the maximum possible horizontal displacement. So if t goes to infinity, right, then we'll get our maximum because it's just going to keep, it could potentially keep going maybe. Let's have a look. So as t goes to infinity, e to the -t on 6 would go to 0. If you put a really huge number in there, you'll see that's very, very close to 0. So therefore, x goes to 90 times 1 minus 0, which equals 90 meters, because this was all in meters and seconds. In part D, we're asked to find the time taken to reach its maximum height. So of course it's going to reach its maximum height when its velocity, when its vertical velocity is equal to 0. So when this thing equals 0. So if I divide by the 15, that's gone. So this whole stuff in the brackets needs to equal 0. Let's add the 4. So 4 plus root 3 e to the negative t on 6 equals 4. Divide by this thing, e to the, it's pretty simple solve. So 4 over 4 plus root 3 log, so negative t on 6 equals log of 4 over 4 plus root 3, multiplied by negative 6. So t equals negative 6 log of 4 over 4 plus root 3. Now before putting this in a calculator, let's predict whether that's a positive or a negative value. So given that it's time, we would really hope it's positive, but we've got this negative out in front, so think about this. Obviously that denominator is bigger than the numerator, so it's a fraction, less than 1, and log of something less than 1 gives a negative value as well. So it's a negative times a negative, so it is positive, which is what we want, and it actually equals 2.16 seconds to 2 decimal places. In part E, we're asked to find the horizontal distance travelled when the particle reaches its maximum height. So that's literally just plugging that value of t that we found in the previous example into that equation. Just for the fun of it, I thought I might do that in exact form. So that's 91 minus e to the negative t over 6. That's just going to be log of 4 plus root 3, because negative 6 log 4 on 4 plus root 3, negative t on 6 equals, so it's negative of that, so that becomes positive over 6. So it's just this log bit. Now e log cancel each other out, so that's 91 minus 4 over 4 plus root 3. Let's make some fractions there. I'll just put the 4 plus root 3 out the front. So this will be 4 plus root 3 over 4 plus root 3 minus 4. So we've got a 4 minus 4 here, so that's just a root 3. So it's 90 root 3 over 4 plus root 3 meters. And in a calculator, that equals 27.20 meters to 2 decimal places. Okay, so we're going to find the maximum height obtained. So this was our vertical velocity equation. We need to integrate to find our equation for our height. So the velocity is the same as dy dt equals 15 4 plus root 3 e to the negative t on 6 minus 4. Now this is, I'm going to go back to the old-fashioned way of doing this. Let's integrate each side. So y equals, with respect to t, I'm integrating both with respect to t. So 15 4 plus root 3. Let's multiply by negative 6 because I'm dividing by negative a sixth. E to the negative t on 6 minus 4t plus c. I might leave the c outside the brackets for now. So we know that initially y equals 0 when t equals 0. So let's find our c. So 0 equals 15 4 plus root 3 times negative 6 e to the 0 minus 4 times 0 plus c. This is 1. So 15, we've got 4 plus root 3 times negative 6 there, plus our c. Let's work that out. So negative 90, 4 plus root 3 plus c. So c would be equal to that thing. If I add that thing to each side, c is equal to 94 plus root 3. So I might put that 15 out. So we've got y is equal to 15 bracket 4 plus root 3 times the minus 6. Almost should have put that earlier. Negative t on 6 minus 4t. factoring out the 15 so that the c is inside the brackets as well makes this plus 6 times 4 plus root 3. Now let's just tidy this all up a bit. I might take a -2 out the front. So let's make that -30 bracket. Let's put the 3, 4 plus root 3 e to the negative t on 6. I've got a -2 at the front, so that's plus 2t minus 3 bracket 4 plus root 3. So to find the maximum height, we just need to put our t into that equation. Again, we could just use our calculator to find that. And in the calculator, I'm getting that maximum height is equal to 26.36 meters to 2 decimal places. It might be fun to do it in exact form also. So we're plugging this time when it reaches its maximum height into that equation. So y is equal to -30 bracket 3, 4 plus square root 3 e to the negative t on 6, so log of 4 over 4 plus square root 3 plus 2 times -6 log of 4 on 4 plus root 3. I'm running out of space there, so minus 3, 4 plus square root 3. Pretty nasty one for exact form, but you know, it's kind of fun. So we've got an e and a log here, so let's have a look at that. So that's going to be 3, 4 plus root 3 multiplied by this thing, so times 4 over 4 plus root 3. So that's a really nice cancellation there. It's not all going to be that nice though, so minus 12 here, log of 4 over 4 plus root 3, minus 3 times 4 plus root 3. Close the bracket. Let's have a look at what we've got now. So this is -30, 12 from that. There's a minus 12 there as well, minus a 3 root 3 there, minus 12 log 4 on 4 plus root 3. So let's see what we've got now. I might actually expand it all out. So 12 minus 12 is nothing, that's gone. -30 times -3 root 3 is 90 root 3, plus now 360, 12 times 30, yep. Log of 4 on 4 plus root 3. And I double checked that in my calculator and got the same answer, so that's done perfectly.